Imagine being a sailor, right? Like you're in the British Royal Navy in the early 1700s. You're way out at sea, and there's this terrifying, mysterious illness just uh, sweeping through your ship.
Oh, it was an absolute nightmare.
Right. It starts with exhaustion, and then your gums start bleeding, your teeth literally fall out, and, eventually it's fatal. Scurvy was killing more sailors than enemy cannons, shipwrecks, and storms combined.
Combined, yeah, it's wild.
And the craziest part is that the medical community back then had, absolutely no idea how to stop it because they didn't know how to properly test a cure.
They really didn't. I mean, they were just guessing.
Exactly. So welcome to this deep dive. Today we are exploring the birth of what is basically the gold standard of scientific truth, the controlled experiment.
Yeah, the fair test.
Right. This is a journey designed specifically for you, especially if you're, studying for a nursing entrance exam right now, like the TEAS or the HESI. Or, honestly, if you're just insanely curious about how we actually know what we think we know.
Which we all should be, honestly.
Definitely. So we're going to look at the mechanics of these fair tests, how manipulating just one single variable while kind of freezing the chaos of the rest of the world is really the only way to prove a genuine cause.
It's a profound shift in human history, if you think about it. Because for thousands of years, humanity just relied on authority or ancient texts or, just casual observations.
All right, like, oh, I took this herb and I feel better.
Exactly. The herb must work. But today, we're going to trace how a few brilliant and sometimes really desperate minds figured out that the world is just too messy for simple observation. We'll break down the core machinery of a valid experiment, some famous historical failures, and those massive misconceptions that trip up even seasoned professionals.
Yeah, those test traps.
Wow.
Okay, let's unpack this with a scenario we all know, just to get the foundational logic down. Think about baking.
Oh, I love baking analogies.
Right. So say you want to figure out why a new cake recipe tastes better than your old one. If you change the brand of flour, crank up the oven temperature, and add an extra cup of sugar all at the exact same time.
And the cake comes out amazing.
Yeah, you have a great cake, but you have absolutely zero new knowledge. You have, no idea what actually improved it. Was it the heat? Was it the flour?
You can't know.
Exactly. To figure it out, you have to isolate the variables. You have to bake two cakes where everything is completely identical except for one single thing.
And that baking logic is the exact mechanical foundation of all experimental validity. But before we dive into the history of scurvy and naval ships, we really need to clearly define the anatomy of this machinery.
The terminology.
Right, the terminology is critical, especially for anyone facing an exam. At its core, a controlled experiment rests on this very specific chain of logic. If you change only one thing and the outcome changes, that one thing is a highly plausible cause.
Okay, so let's lock in those variables for everyone listening. The thing you deliberately change, like the sugar in the cake, or say the specific dose of a new drug in a clinical trial, that is your independent variable. I always remember it as the I variable, like I changed the independent variable.
That's a great trick.
Yeah.
I change it.
And the outcome that you measure as a result, the taste of the cake or a patient's blood pressure dropping, that is the dependent variable. Its value literally depends on what you manipulated.
Exactly. And just as important are the controlled variables or the constants. These are the elements you keep identical. The oven, the baking pan, the room temperature.
Right.
But this raises a really important question and a very common misconception. People often hear the phrase controlled experiment, and they assume it means the researcher is playing God, keeping absolutely every single atom in the room exactly the same.
Which is completely impossible outside of, a vacuum chamber.
Yeah.
I mean, if I'm doing a study on 100 different human beings, I can't keep their genetics, their breakfast, and their sleep schedules completely identical. Does that just ruin the experiment?
Well, no, it doesn't, because the goal isn't to freeze the entire universe. The goal is to keep everything except the independent variable as consistent as practically possible between your groups.
Okay, so just as close as you can get it.
Right, so that any major differences in the outcome can confidently be tied back to your intervention. Which actually brings us to the structure of the groups themselves. You need an experimental group that receives the intervention and a control group that does not.
Wait, I really want to highlight something here because I've seen so many people get tangled up on this exact definition.
Oh, the control group trap.
Yes. When the term control group is thrown around, it sounds incredibly active. Like, it sounds like the group that the scientists are controlling with their special new treatment.
It is the exact opposite, and I see this trip people up on exams all the time. The control group is the untreated baseline.
The baseline. What?
Yeah, they might get absolutely nothing. They might get the standard existing care, or they might get a placebo, but they represent the state of the world without your new independent variable.
Because without that baseline.
You cannot tell if an observed change was caused by your treatment or if it just would have happened naturally anyway.
Right. Let's use Ivan Pavlov as an example. The famous 1890s classical conditioning experiments with the salivating dogs.
Oh, that's a perfect example. So Pavlov wanted to know if dogs could learn to associate a totally neutral stimulus, like a metronome or a bell, with being fed.
Right.
The independent variable, the thing he manipulated, was the pairing of the bell with the food. The dependent variable was the amount of saliva the dog produced, which he actually measured with a physical apparatus.
Poor dogs, but... Okay, so his constants would be the environment, the feeding schedule, the room the dog was in. But what was his baseline?
Well, the control condition was presenting the bell alone, without ever pairing it with food.
Oh.
He had to establish that baseline just to confirm that dogs don't naturally start drooling every time they hear a bell ringing. The control proves that the bell itself means nothing until the experimenter steps in and pairs it with the meat powder.
That makes total sense. So we have the mechanical recipe. We isolate the independent variable, measure the dependent variable, keep the constants constant, and use a control group as a baseline. But go back to those sailors. How did humanity actually figure this out?
Well, if we connect this to the bigger picture, the philosophical groundwork goes back to Francis Bacon in the early 1600s. In his 1620 work, Novum Organum, he essentially pleaded with the scientific community to stop just observing nature passively.
Like, get in there and mess with it.
Exactly. He argued for systematic manipulation, but the first truly documented controlled medical experiment happened a century later, in 1747, thanks to a Scottish ship surgeon named James Lind.
Aboard the HMS Salisbury. So Lind is surrounded by this horrifying scurvy outbreak. What makes his approach different from literally every other doctor at the time?
Well, other doctors were just throwing random remedies at patients based on superstition or like ancient Greek texts. Lind decided to run a fair test. He took 12 sailors who were already sick with scurvy. He made sure their cases were as similar as possible to control for severity, and then he divided them into 6 pairs.
6 pairs. Got it.
Crucially, Lind kept their diet and their physical living conditions on the ship identical. Those are our constants.
And then he introduces the independent variable, the treatment.
Yes. He gave each of the 6 pairs a different suspected remedy. One pair got a quart of cider a day, another got vinegar, another got seawater.
Yikes. Seawater.
Rough. One pair got a weird mixture of garlic, mustard seed, and balsam of Peru, and another pair got a dosage of sulfuric acid.
Sulfuric acid. I mean, I know the 1700s were brutal, but giving a dying sailor sulfuric acid is terrifying.
It really shows you how desperate they were, but the final pair received 2 oranges and a lemon every day.
The citrus.
Right. Within less than a week, the pair given the citrus fruit recovered so dramatically that one of them was put back on active duty, and the other actually became a nurse to the rest of the sick men.
Wow.
None of the other pairs showed meaningful improvement.
It is this brilliant, elegant little miniature experiment. I mean, he manipulated one variable, held everything else constant across comparable subjects, and discovered a life-saving truth. But from what I understand, Lind's experiment, as great as it was, it didn't really have the math behind it to prove it wasn't just a total fluke.
That is the missing piece, yeah. Lind had the logic, but not the statistics. The mathematical machinery that actually verifies a result came much later, in the 1920s and 30s.
Okay, who is that?
There was a statistician named Ronald A. Fisher working at the Rothamsted Experimental Station in England. He was staring at decades of messy agricultural data, trying to figure out which fertilizers actually worked best on crop yields.
And agricultural data has to be a total nightmare.
Yeah.
Because, like, if you just compare a field with fertilizer to a field without it, you aren't just comparing the fertilizer. One field might have inherently better soil, or different drainage, or more sunlight.
Exactly.
They're totally contaminated by what we call confounding variables, right?
Yeah.
Things outside your control that just mess up your results.
Right, and what's fascinating here is how Fisher actually solved the problem of those confounding variables. Because he couldn't just put a farm field in a sterile laboratory.
Right, it's outside.
So in his 1935 book, The Design of Experiments, he formalized 3 massive concepts: replication, factorial design, and most importantly, randomization.
Okay, let's break those down. Replication makes sense. You don't just test one patch of dirt, you test many to make sure an anomaly doesn't skew your whole study. But what exactly is factorial design?
So factorial design is a mathematical way of varying more than one factor at a time, but in a very structured grid. Let's go back to your cake analogy.
Okay.
Instead of doing 100 experiments just on flour and 100 just on sugar, you test them simultaneously in different combinations. This allows you to see not just what the flour does, but the interaction between the new flour and the new sugar.
Oh, wow. So it's way faster.
It makes experiments vastly more efficient and much closer to real-world complexity.
Okay. And randomization. Because random assignment feels like the absolute magic bullet of modern science. How does just flipping a coin fix the problem of bad soil or different genetics?
It is brilliant in its simplicity. When you randomly assign subjects, whether they're plots of land or human patients, to your experimental and control groups, you take all those unknown, unmeasured differences and you spread them out evenly.
Like shuffling a deck.
Exactly. If there's a certain genetic quirk in your patient pool, random assignment ensures that roughly half of the people with that quirk end up in the control group and half end up in the treatment group. The confounds mathematically cancel each other out.
Here's where it gets really interesting. Because Fisher is famous for testing this exact mathematical rigor in what has to be the most British experiment of all time, the lady tasting tea experiment.
Oh, yes, a
A
classic.
colleague of his claimed she could taste whether milk was poured into her teacup before or after the boiling water was added. Now, most people would just roll their eyes or, hand her one cup and say, guess.
But Fisher realized that if you only hand her one cup, she has a 50% chance of being right just by guessing.
Exactly. So he actually designs a rigorous test. He prepares 8 cups of T4 with milk first, 4 with water first. He presents them to her in a completely random, blinded order. And the math he developed for this wasn't just to see if she was right, but to calculate the exact probability that she could have categorized all 8 cups perfectly just by sheer luck.
He was testing the statistical significance of her claim.
Right.
And that mathematical framework literally changed the world. Once we combined Lynn's controlled logic with Fisher's statistical randomization, we had a method that could reliably save millions of lives. Fast forward to 1954, and we see the ultimate triumph of this method, the Salk polio vaccine trial.
This trial is just mind-blowing in its sheer scale. We are talking about roughly 1.8 million American school children participating.
It remains one of the largest public health experiments in history. Children were randomly assigned to receive either the actual Jonas-Salk vaccine or a saline placebo injection, which, remember, was our control baseline. And crucially, it was a double-blind design.
Okay, double-blind meaning neither the patients nor the doctors knew who got what. Now, I totally understand blinding the patients, or the parents in this case, because of the placebo effect. If you think you got the real vaccine, maybe you behave differently. But why hide it from the doctors? I mean, they're medical professionals.
Because doctors are human, and human expectation is a powerful confounding variable. If an evaluating doctor knows a child received the real vaccine, they might unconsciously evaluate their symptoms differently. If that child comes in with, say, mild muscle weakness, the doctor might think, well, they are vaccinated, so this must just be a standard flu, not polio.
Wow. So their bias literally skews the data.
Exactly. Blinding removes the researcher's bias from the measurement. And because the assignment was random and blinded, when the vaccinated group showed a massive reduction in paralytic polio, scientists could definitively prove causation.
Okay, wait, I have to push back here for a second. If Fisher literally wrote the book on experimental design in 1935, and Salk flawlessly executed this massive double-blind trial in 1954, how on earth did the thalidomide tragedy happen just a few years later?
Yeah, that is the tragedy of regulatory lag. Science knew how to do a fair test, but the law didn't require it yet.
Oh, wow.
In the late 1950s and early 1960s, thalidomide was marketed across West Germany and dozens of other countries as a remarkably effective sedative and anti-nausea drug, and it was highly recommended for pregnant women experiencing morning sickness.
But they hadn't run randomized controlled trials on pregnant women, right?
They had not. The animal testing protocols of the era just didn't rigorously test for teratogenic effects.
Teratogenic meaning it causes malformations in a developing embryo.
Correct. And the evidence they relied on for human pregnant women was largely observational and anecdotal. Doctors were essentially observing that their patients took the drug and felt less nauseous.
So they were basically relying on, well, my neighbor took this and her morning sickness went away.
Pretty much.
It is horrifying that observational evidence was considered sufficient to put a drug into global circulation.
It was a catastrophic failure. Because observational studies can only show a correlation that two things are happening at the same time. They cannot isolate variables. Because there were no properly controlled trials to detect the devastating effects on fetal development, thalidomide was widely consumed, resulting in an estimated 10,000 or more children worldwide born with severe limb malformations.
That is just heartbreaking. And it fundamentally altered how we approve medicines, didn't it?
Completely. The thalidomide tragedy directly catalyzed the 1962 Kiefer-Harris Amendment in the United States. It fundamentally changed the FDA. For the first time, drug manufacturers were legally mandated to prove not just that a drug was safe, but that it was efficacious.
They actually had to prove it worked.
Yes, and they had to prove it through well-controlled, randomized clinical trials before hitting the market. The legal standard finally caught up to the scientific standard.
This kind of brings us back to something we touched on with the Salk trial, the double blinding. We've talked about how isolating physical variables like the temperature of the oven or the diet on a ship is vital. But why is the human mind such a unique, contaminating variable?
Well, this raises a really important question about human psychology and research. When living subjects know they are being observed, their behavior fundamentally changes.
Oh, right.
The classic illustration of this is the Hawthorne effect, named after a series of studies conducted at the Hawthorne Works electrical plant in Cicero, Illinois, back in the 1920s and 30s.
Oh, the factory lighting study. This one is fascinating.
Mm.
So researchers went into this factory wanting to test a simple, independent variable, the brightness of the lights. They wanted to see how it affected the dependent variable worker productivity. So they crank up the lights and boom, productivity goes up. So like a clear cause and effect.
It seemed perfect, yeah. But then, just to be thorough, they decreased the lighting. And productivity went up again.
Wait, really?
Yeah. They changed the lighting back to normal, and productivity still went up. Even the control group, whose lighting was never altered, showed increases in productivity.
Because the workers weren't responding to the lumens of the light bulbs. They were responding to the fact that researchers with clipboards were standing on the factory floor watching them assemble relays. The awareness of being studied was this unmeasured, invisible psychological variable that just contaminated the entire test.
Precisely. And it isn't just a human phenomenon. Look at Clever Hans.
The math-doing horse
Uh-huh.
from early 1900s Germany. People genuinely believed this horse could solve arithmetic. You would ask him, what's 4 plus 3? And he would tap his hoof 7 times and stop.
He was an absolute sensation. But a psychologist named Oscar Funkst approached this as an experimental design problem. He varied the conditions. He ran a test where the person asking the question didn't actually know the answer themselves, and another where Hans had blinders on and couldn't see the questioner.
And the moment the horse couldn't physically see the questioner or the questioner didn't know the answer, Hans suddenly lost all his math skills.
Exactly.
He wasn't doing addition, he was reading the room. The handler was giving unconscious, microphysical cues like tensing up as the hoof taps got closer to the right number and then relaxing when the horse hit the right answer. The horse just learned to stop tapping when the human relaxed.
That is the Clever Hans effect, and it is the ultimate argument for blinding in research. If you don't blind your experiment, humans, and apparently animals, will subconsciously cheat the results.
That's incredible.
But this need for intense control, for blinding, for sterile environments, it introduces one of the biggest ongoing debates in science: the tension between internal and external validity.
Okay, I know ecological validity is a big buzzword in psychology. Can you break down what those terms actually mean in practice?
Sure. Think of internal validity as your confidence in the laboratory. When you tightly control every variable in a sterile, perfectly white room, you have extremely high internal validity. You can confidently say, variable A definitely caused outcome B in this room.
Okay, got it.
But critics argue that by stripping away all the messy, chaotic context of the real world, you destroy the experiment's external validity, which is also known as ecological validity.
So, like, you might prove that a certain memory technique works flawlessly when a college student is sitting alone in a silent, perfectly climate-controlled lab. But that tells you absolutely nothing about whether that memory technique will actually work when that same student is exhausted, sitting in a loud coffee shop stressed about their rent.
Exactly. You isolated the cause, but you made the environment so artificial that the findings might be completely useless in the real world. It is a constant tightrope walk for researchers.
So what does this all mean for the concept of truth? I mean, if human bias is constantly threatening to leak in, and our perfect lab settings might not even apply to the real world, does a single successful controlled experiment ever actually prove anything with a capital P?
The short answer is no. And over the 20th century, philosophers of science fundamentally shifted how we talk about this. Thinkers like Karl Popper pushed back hard on the idea of definitive proof.
Popper is the one with the swans, right? He argued that experiments can't actually confirm a theory is universally true. They can only fail to falsify it. Like you can observe 10,000 white swans, and it still doesn't prove that all swans are white because the very next swan you see could be black.
That is the core of falsifiability. Because of that logic, the scientific community moved away from the idea that an experiment delivers absolute certainty. Today, a controlled experiment is viewed as a procedure that allows for a statistically defensible inference about a cause, given a stated margin of uncertainty.
And they measure that uncertainty using things like p-values. I know p-values terrify a lot of students. How should we actually visualize what a p-value is doing?
Think of a p-value like a suspicion meter.
Suspicion meter, okay.
When a researcher runs an experiment, they start with a null hypothesis. The assumption that their new drug or intervention does absolutely nothing, and any difference they see is just random luck.
Right.
The p-value measures how surprising their data would be if that null hypothesis were true. If a clinical trial results in a p-value of 0.05, it means there is only a 5% probability that you would see these results just by sheer random chance.
Well, it doesn't mean you're 95% right. It just means the data is highly suspicious if your drug was actually useless.
Exactly.
And researchers also use confidence intervals, which is basically them saying, look, we can't give you a perfect exact number, but based on our data, we are 95% confident the true effect of this drug falls somewhere between this lower number and this upper number.
Yes. They are quantifying their own uncertainty. And this brings us to the replication crisis that made all those headlines in the 2010s.
Oh, right.
A massive initiative called the Reproducibility Project tried to rerun roughly 100 high-profile psychology experiments. A large portion of them failed to produce the same results or showed much weaker effects than the original studies claimed.
Which naturally leads people to panic. If the gold standard of evidence is failing to replicate, should we just, stop trusting science altogether?
The irony is that the replication crisis is actually science functioning perfectly.
How so?
Well, a single published paper is just one data point. True scientific confidence is built slowly.
Right.
It requires replication by independent teams, increasingly larger sample sizes, and rigorous statistical checks. A single experiment doesn't give you the truth. A consensus of replicated experiments does.
Okay, let's bring this all back home for you listening. Whether you're about to sit down for your TEAS or HESI exam, or you're just trying to survive the daily avalanche of news headlines. What are the core takeaways? First, remember the baking analogy. To find a true cause, a valid experiment manipulates exactly one independent variable while holding all the controlled constants steady.
Second, do not fall for the control group trap.
Yes, please.
The control group is your baseline. It is the untreated group or the placebo group used purely for a comparison.
Third, remember James Lynn and thalidomide. Observational evidence can give you a correlation, two things happening at once, but it takes a randomized controlled test to actually prove causation. And finally, you have to use blinding to defeat the human element. Whether we are factory workers or horses doing math, the mere act of being observed changes our behavior.
And the real-world application of this is incredibly empowering. Tomorrow, when you see an article claiming people who drink green tea live 5 years longer, you will immediately recognize that as an observational correlation. But if you read, a double-blind, randomized controlled trial shows this new medication lowers cholesterol by 20%, you now understand the rigorous mechanical machinery that makes that second claim so much more trustworthy.
You aren't just taking someone's word for it anymore. You can actually see the gears turning under the hood of the research. Which leaves us with one final, slightly provocative thought to chew on.
Oh, boy.
We talked extensively about the Hawthorne effect, how knowing you are being watched fundamentally alters how you act. Think about the modern digital world we live in right now. We are surrounded by workplace keystroke monitors, algorithmic social media feeds tracking our scroll speed, and smart devices listening to our environment.
Constantly.
Are we currently living inside a massive, completely uncontrolled Hawthorne experiment? Is it possible that our true, natural human behavior doesn't even exist anymore, simply because we were always so consciously aware that we were being observed by the algorithm.
That is the ultimate confounding variable, a chilling thought.
Something for you to mull over the next time you're scrolling through your feed. Thanks for taking this deep dive with us. Keep questioning the variables, look out for those confounds, and we'll catch you next time.